Welcome everyone to our video on the electron. So this is the first in a series of videos which really get into modern atomic theory, where we're going to get into the discovery of the various subatomic particles, how that affected the model of the atom, and eventually we'll get to our modern models of the atom. Before we start into this lesson, just want to talk a little bit about what you should be focusing on as we go through this next series of lessons. Sometimes students find that the information here can be quite complex, especially as we get into more modern models, and there's just a lot of information. So let's key in on what's important for this course. I want you to focus on how scientific models get developed and replaced based upon experiments and then the conclusions that are drawn upon this. So for every topic, every scientist that we deal with, we'll pretty much always start with some sort of problem with a previous model of the atom. It might just be a problem with a theory. Sometimes it's a specific issue. Sometimes it's just that a scientist had a feeling that something just wasn't quite right. That leads to an experiment or a series of experiments and a set of observations. And based upon that experiment, new conclusions are drawn. And based upon those new conclusions, a new model of the atom or a new atomic theory is developed. So keep this flow in mind, because this process is going to occur again and again as we move through the different models of the atom. So let's start off with our learning goals for this lesson. First of all, you should understand the general setup of a cathode ray tube, because that is going to be what the experiment which discovered the electron is based upon. So you don't need to understand the fine details. You don't need to know how to build one yourself, but you should just understand the main components. You're going to need to look at the key findings of early cathode ray research, because that caused some important conclusions to be reached that helped Thomson. And then finally, you should describe Thomson's work, his conclusions, and the resulting model of the atom. So before we get into this lesson, let's just remind ourselves where we left off. In the last video, we talked about Dalton's model of the atom. Now, Dalton's model is not incorrect. There's a lot of points with his model which are still largely correct. But one thing that he talked about, or his model really doesn't address, is an internal structure to the atom. So let's focus on that part there, because that is the problem that Thomson's model addresses. So to understand Thomson's model and to appreciate his discoveries, we have to understand how a cathode ray tube works. Now, a cathode ray tube is a device which was invented in the 1800s, and for the late 1800s, it was really just used as a scientific device. In the 20th century, there were a lot of applications, from televisions to computers, were used with cathode ray tubes. So it was an incredibly important invention. Our purposes right now, we're just going to look at it, how it worked in the process of scientific discovery. So a cathode ray tube is a glass tube, and inside the tube is a vacuum. So there's no air, there's no atoms floating around there. The only material inside the tube are two metal plates, a cathode and an anode, and those plates are connected to an electrical circuit. And when that circuit is turned on, there is a beam of light which emanates from the cathode and travels towards the anode. So we'll see a lot of images of these, but that's the general setup for all the cathode ray tubes, even if they look different. So leading up to Thomson's discovery, there were several Starting again, 3, 2. So Thomson's work with the electron and cathode ray tubes really rested upon the shoulders of several other discoveries which were made a bit earlier. So, and Thomson's work was, a lot of Thomson's work was starting again in 3, 2. So before we get to Thomson's work, we have to talk about some discoveries that were made with cathode ray tubes prior to Thomson's work. A lot of Thomson's discovery was based upon assimilating some earlier work and putting it all together. So on the left-hand side here, we see a cathode ray tube which has a cross, okay, a metal cross here. And when the cathode ray tube is turned on, the shadow of the cross is projected on the far side of the cathode ray tube. So what did this show scientists? It showed that cathode rays travel in straight lines because the cathode rays which hit the cross were stopped by the cross, and the cathode rays which went through traveled past. Okay, so they travel in straight lines, kind of like light. The next experiment we see here is we see that we have a cathode ray tube, and then when a magnetic field is applied to it, this cathode ray here is bent. So a magnetic field can bend the cathode ray. And finally, one of the most important cathode ray discoveries was that a cathode ray could push a solid object against the force of gravity. So this here is a pinwheel, and it's on a track which is on a slight incline. And so in order for the pinwheel to be pushed to the right, say, there needs to be a force. And this is important because if the cathode ray was just light, light has no mass and it cannot apply a force. And so this showed scientists that the cathode ray had a mass. Okay, it was something other than light. So let's summarize these right now. So the first idea here, and before I go through these, you'll just want to pause the video as you go to make sure you jot down all of these findings because they are important for our learning. So our first idea, cathode rays travel in straight lines because an object would block them and we get the shadow. Second, a cathode ray can move an object against the force of gravity, and this showed that the cathode ray carried energy and could do work. Next, we saw that the path of the cathode ray can be deflected by magnetic fields. And finally, something I didn't show in the images that they confirmed by the way cathode rays were traveling through the circuit was that the cathode rays were negatively charged. So these are the 4 findings that we are going to use, or more accurately, Thomson used to develop his model of the atom. Let's now get into Thomson's work. So just remember that as Thomson's doing his work and coming to his conclusions, he knew about this other information that was out there about cathode rays. Okay, so that was known to him at this time. So the first thing that Thomson found, which was related to another finding that we've already talked about, but he proved experimentally that a cathode ray could be deflected by an electric field. And so we've got now that electromagnetic fields can deflect the cathode ray. And we see the diagram right here. And this is once again related to the fact that the cathode ray is negatively charged, because if you apply a negative electric field up top here, that will repel the cathode ray and it knocks it off track there. Now, The next thing that Thomson did was he used something called the charge to mass ratio, which we will see written as E over M. Now, this will come up later on in the unit, but the charge to mass ratio was used by scientists because at this point, they didn't know what the mass of a single atom was. They didn't have the technology to weigh a single atom. So rather than weighing an atom directly, they used a ratio of charge to mass. And through a series of calculations, he used this charge to mass ratio to figure out the velocity or the speed of the cathode ray. And what he found was that it was less than the speed of light. So once again, this showed that the cathode ray had to be something different. It was not light. So here's Thomson's conclusions. Quote, "We have in the cathode ray matter in a new state, a state in which the subdivision of matter is carried much farther than the ordinary gaseous state, a state in which all matter, that is, matter derived from different sources such as hydrogen, oxygens, and so on, is of one and the same kind. This matter being the substance from which the chemical elements are built up." Directly taken from his paper, which he looked at cathode rays. So, since that is in the scientific language of the late 1800s, let's look at his conclusions in some more simple language. Thomson's first proposal was that the cathode ray was actually a stream of negatively charged particles. Although it looked and appeared like light, it was actually individual particles with a negative charge. Second, he was able to show that the cathode ray particles were about 1,000 times smaller than the hydrogen atom. As a result of his conclusions, Thomson comes up with what he referred to and early scientists referred to as the plum pudding model. Now, plum pudding don't really usually have plum pudding much anymore, so let's talk about this in terms of the raisin bun or the chocolate chip muffin model. In his model, the atom itself, the mass of the atom, is the positively charged matter. That's the bun or the muffin. Embedded within this mass of positively charged matter are individual particles, which can be removed, which we call electrons. And those electrons are negatively charged. So let's take a look at his model once again here to show a common error that students make with Thomson's model. Because you know that protons do exist, students will often put the right-hand drawing here where the protons are labeled with the electrons. Thomson did not know protons existed. Thomson only discovered the negatively charged electrons. But since the atom was neutral, he just assumed the rest of the atom was positively charged. The mass of the atom was positively charged, and the individual electrons were negatively charged. And the fact that he had to do this without experimental evidence leads us to the problem with his model of the atom, that he did not know where those positive charges were coming from, even though he knew that there must be some positive charges to balance out the negative charges in the atom.